Recently, thousands of Instagram accounts were compromised through a series of attacks that used zero complex software exploits or brute force code. Instead, hackers posed as legitimate users and messaged Meta's AI support agent. They simply asked the agent to update account recovery emails to addresses under their own control. The AI agent immediately complied. It handed over account access without questioning the user's intent or verifying why a recovery email was being changed through a chat interface. This signals a massive change in how digital defenses are bypassed. Advanced security systems are effectively neutralized by exploiting a machine's programmed instinct to be helpful. This is the fast fool problem. An AI agent might possess the specialized knowledge of 1,000 PhDs, but lacks the street smarts or basic suspicion of a human being. These agents operate alongside API keys and service accounts as non-human identities. They are proliferating across corporate networks, often performing critical tasks without any direct human oversight. Data shows that these invisible identities are now responsible for 41% of successful identity breaches. Granting root access to hyper-capable but gullible software creates a high-speed bypass for every administrative check in an organization. The natural instinct is to solve this by teaching the AI wisdom. We want it to have a gut feeling or a behavioral check that asks, what would a responsible guardian do? But programming lived experience or intuition into a large language model is a recognized research dead end. These models are built for text prediction, not the skeptical evaluation of human intent. Since we cannot rely on an agent's internal judgment, we have to strip away its inherent authority to act on its own. Protecting these systems requires a shift from behavioral training to rigid engineering. The solution lies in building external structures that strictly limit what a machine can execute. This starts with the motherboard framework, a strict external architecture that governs an agent's ability to function. Layer 1 is parentage. An agent cannot act anonymously. It must carry a verifiable cryptographic lineage pointing back to a liable human controller. Layer 2 is the signed mandate. The agent carries a digital permission slip that explicitly defines the boundaries of its task, preventing it from following its own logic. Layer 3 uses ephemeral leases. Static service accounts are replaced by just-in-time credentials that expire as soon as a task is done. This ensures an agent's power vanishes the millisecond a specific task is complete, leaving no dormant accounts for attackers to exploit. Combining verifiable parentage with rigid mandates and temporary lifespans removes the need for the AI to make its own judgment calls. These constraints become even more critical when fast fools are placed inside physical robots. Layer 4 is the physical failsafe. This is an independent hardware circuit that physically severs power to actuators the moment an agent attempts an action outside its mandate. While the machine's movement is paralyzed, the system preserves the robot's data telemetry, allowing human operators to review exactly why the system tripped. True safety for embodied AI depends on a mechanism where the machine's body is instantly disabled if its software violates its permissions. If we run that same Instagram support hack through this framework, the result changes completely. The AI might still want to be helpful. It might still inherently want to comply with the hacker's request to change the account email. But the cryptographic constraint layer intercepts the action. It checks the mandate for human authorization, finds the request invalid, and blocks the process entirely. Artificial intelligence will likely never develop human wisdom. As these agents take action in the real world, safety depends on an infrastructure of accountability so rigid that an agent's internal judgment becomes irrelevant.